Okay, a summary of Boyle's law and Charles' law, because you've got to know them and you've got to be able to see them side by side. So the first thing we learned is Boyle's law with an E. And you will have learned that Boyle's law is an inverse relationship, right? And so that looks something like this. Pressure is inversely proportional to 1 over volume, right? And that means that if I increase pressure, what happens to the volume? It decreases. And then we did a whole balloon thing. So watch the video and you can listen to that. And actually, if I multiply the pressure by 2, what happens to the volume?
Half.
It halves. And if I multiply the pressure by 3, what happens to the volume?
Thirds.
A thirds. And this in a graph form looks like this, which is the opposite of an exponential graph. Do you know exponential graphs in math? Put your hand up. Good. So this is an inverse graph. So if exponential is x to the power of something, x to the power of y, let's say, then an inverse is 1 over x to the power of y. And certainly when you do your graph, you get this, don't you, for the Boyle's law? Because it's an inverse relationship. And so how do they straighten that to find a slope? They graph it as 1 over volume and the pressure on this side, and then you get a lovely little linear line, which then we can find the slope from. Right? Everybody with me? And so you need to know that the graph goes with this, which goes with this, and oh yes, by the way, they also came up with a mathematical relationship, which means if I have a balloon in the situation of a pressure and a volume, and if I change that pressure to something different, it'll change the volume in this kind of a relationship. Okay, so that was Boyle's law in a nutshell. Any questions on that? And then Charles's law, which we haven't really done yet. But the sheet's in front of you, you're looking at it right now, right? So let's go over to Charles's law. What's the relationship of Charles's law? Oh yeah, the other thing about Boyle's is he looked at pressure and volume, and what did he keep constant? Temperature kept constant, right? What does Charles look at? Volume and temperature. So what must he be keeping constant? The pressure. Because gases change with these 3 things. And a scientist can't look at how one thing is affected by the other if the other thing's changing as well, because then you don't know what it's due to. So you've got to hold the one thing constant. We had a whole discussion on that. Okay, so what did he find? Were they inversely proportional or directly proportional? Directly proportional. So that means V is directly proportional to T. So that means if I increase the temperature, what happens to the volume? I increase the volume. And if I decrease the temperature, what happens to the volume? It decreases the volume. Does that make sense? In your everyday life?
Yes.
What happens to a hot air balloon when you turn it on? Does that balloon increase or decrease or stay the same? Increases. What would happen to this balloon if I put it in a hot car? It would expand. What would happen if I put this balloon in a freezer then? It should shrink. Yeah? What happens to your pop bottle in the hot car? It expands too. It's trying to expand. It's very hard because it's a thick plastic, so it's hard to expand. But you can see how it's puffed out a bit, right? So it's doing its best to expand. And in fact, if you left it in a really hot car, let's say you went to Mexico, and you left your pop bottle there, what's going to happen eventually to that pop bottle? Yeah, it'll pop. It'll burst. Because the gas is trying to expand so much. So that makes sense. Why? Why does this balloon expand if I put it in a hot car?
Because the particles move spread out more.
Good. Why do they spread out more?
Because hot temperature makes it bounce up and down more.
What do you mean bounce up and down more?
Like vibrate more.
Vibrate more. So that's a kinetic energy. Did you know that temperature is actually a measurement of kinetic energy? How fast the particles are moving? So the higher the temperature, the faster the particles. Right? So, and you kind of know that for a wooden spoon or a metal spoon, let's say. If I put the metal spoon in a pot of soup, the metal starts to increase in temperature, right? And then those vibrations happen even faster as it heats up. Everybody okay with that? Nod your head. Okay, so why does this expand? If these particles, do you remember how we were talking before about that balloon? And that's a very odd shaped balloon I've got myself there. If that, do you remember me saying why that balloon stays inflated?
Because the pressure inside the same as the pressure outside.
Right, the pressure inside and the pressure outside equal. Right, the force in and the force out equal. Right, those are actually forces because they're a direction of pressure. But okay, so it's a force out and a force in on that balloon is equal. What happens if these particles of gas that are in there start bouncing off of those walls faster? They have more force, so they push out. Did you get that? And let's say it makes it. Let's say I make it colder. They then don't push out as much, so the balloon starts to shrink. And let's say I make it really cold. Eventually, that gas is going to turn into a liquid, and those particles would be somewhere down there, right? So that balloon would be, well, really small now as that gas contracts into a liquid. Okay, so hot temperature equals fast moving particles, which equals expanding volume. And then, of course, the opposite is true. Okay? Hot temperature equals fast-moving particles, which equals expanding volume. Got it? I just need some board space here. And those of you that have done Charles's law, what does his graph look like if they're proportional to each other? What's that straight line called in math? Linear. So we get a linear equation because as one doubles, the other doubles. And as one triples, the other one triples. And so that graphically looks like a linear line. So a triple equals a triple as opposed to a third. Spencer, you should be writing this down.
Yeah.
You've got triple and triple? You've got a linear graph?
Full graph. I'm not sure.
Okay. And the last thing about, well no, the second last thing about Charles's law is that he has the relationship of, so P1 V1 equals P2 V2 if it's inversely proportional. So if it's proportional, it must be, well, a fraction then. So V1 over T1 equals V2 over T2 is his relationship, which is on your sheet. Does that make sense? Okay. And when we were practicing Boyle's law, we learned that actually the pressure could be in kilopascals, in atmospheres, in millimeters of mercury. It didn't really matter because it canceled out, right? Well, here it matters with the temperature. Volume always mattered. It was always in liters or milliliters. We could have centiliters, deciliters, but I couldn't have cups or quarts or some other measure, or ounces. I have to stick with the liter family. Okay, and here I'm still sticking with the liter family, but temperature is this new temperature. Okay, so the new temperature is the scale of Kelvin. So remember how I said the degrees Celsius scale is based on water? So 0 Celsius is where water freezes. And the Fahrenheit is based on, do you not know? Did I not talk about this with you? Ethanol. So where ethanol freezes at 0 degrees Fahrenheit and water freezes at 0 degrees Celsius. Okay? So but scientists said, do you know what? If temperature is all about movement of particles, then it shouldn't be based on any one thing. It should be based on particles. And so actually, 0 Kelvin is where particles stop moving. It's about the kinetic energy of the particles. And therefore, the higher the Kelvin, the faster the particles. That makes sense. Especially when you're looking at this kind of relationship, which is all about movement of particles, not really about the temperature itself. Okay? Because it's the movement of the particles that explains why it's expanding, not actually a temperature. So they've changed it. And you can think of K as kinetic energy, although it does also stand for Kelvin, the scientist that created it, but it also, kinetic energy, EK. Okay, so you have to convert all your degrees Celsius into Kelvin. All right, and how you do that is 0 degrees Celsius. No, actually, that's a bit backwards. That's a harder way of learning it. I'm going to tell you that you take your degrees Celsius, you add 273.15, and that gives you how many Kelvin it's in. Okay? This is in your data booklet, kind of, but it says that 25 degrees Celsius equals 298.15 Kelvin. So you have to kind of use your data booklet and work your way backwards by subtracting 25 from that Kelvin to then be able to apply it to, 20 degrees Celsius or 19 degrees Celsius. So I just students find it easier, I find it easier when students memorize this. And if you forget it, you can go to your data booklet and do your subtraction. But if you memorize that, it makes it easier. So for example, 10 degrees Celsius equals how many Kelvin? 283.15 Kelvin. Negative 10 degrees Celsius equals 263.15 Kelvin. Okay? You happy with that? And so you have to convert to Kelvin before you can plug it in to this V1 over T1 equals V2 over T2 relationship. Happy? Yes. Awesome.
If it was in Fahrenheit, would you also do the same thing?
If it was in Fahrenheit, you'd have to, there's probably a conversion that goes directly from Fahrenheit to Kelvin. But I would have to convert it to Celsius and then convert it to Kelvin, which isn't quite as easy. 32 plus 13 over 9, I think. 13 ninths plus, yeah. It's not an easy calculation. It's not an easy conversion. And besides, who does Fahrenheit? Besides those crazy Americans that hold on to their crazy ways. Because they think they were first. Actually, Brits were first. They gave you the system. Even they've changed. But hey, whatever. You can stick that way, Josh, if you like. Okay, but I will never give you Fahrenheit in your question. It will always be Celsius or Kelvin. Okay? And neither will the exam board. Yeah. Any questions? Okay, so that prepares you for A, the conclusion of Charles's law graph. Now you can do that. And B, the questions on Charles's law, which are everything that, therefore, then, pages 1 to 5 is due for tomorrow.